Start recording. There we go. So for anyone who is tuning in online, if you miss Friday's test, you will get a version of the test that includes section 5.7 that you will need to study on your own. And you're writing the test next week because you get extra study time. So let us now go to here. Do I have that printed out? I do not. Oh, that's unfortunate. That's okay. We can make that happen. Get out your review. Everyone get out your review. There we go. I need acid base 2. I need review. Review. That's the one. File print. And we're not going to the printer. We are going to OneNote. Okay, print. There we go. Current section. There we go. Okay. Copy. Paste. Okay. Sorry, it's having a little hissy fit here. All right, here we go. Questions from the review. I know a couple people had questions at least. What do we got? Yes.
76.
76. All right. $76. Which of the following salts will produce a solution with the lowest pH? And so we want everything here. None of the sodiums are going to hydrolyze, right? Sodium. No. Did I press record? Let's check. Yes, I did. Yay. Okay. No. So we need to look at the anions and say which of them will produce the most acidic solution. Does NO3 hydrolyze?
Yeah.
No. And so therefore this salt will give us a solution of pH equal to, if there's no hydrolysis, 7. Excellent. Now, if we have HCO3, HCO3 is amphiprotic, yes? So we have amphiprotic, and in fact, all of them are amphiprotic. So let's go take a look on our data booklet for all of those and their strength as an acid, okay? Because we're looking for the one that has the lowest pH, the most acidic. HCO3, HSO3, and H2PO4. I'm guessing it's HSO3, but let's check. We want HSO3. Well, there's H2PO4 in yellow. And we have HCO3 in yellow. And HSO3 is here in yellow. So out of those 3, it would be HSO3 that is the most acidic because it is the highest Ka value. Does that make sense? Cool. Highest Ka of the amphiprotic anions. Yes. 32. When selecting the indicator for any titration, how should the indicator endpoint compare to the titration stoichiometric point? Let's just be clear what a stoichiometric point is. The stoichiometric point is the same as the equivalence point. It is the point at which the stoichiometry is perfectly fulfilled and there is no excess of one or the other. Yeah? Should the endpoint and the equivalence point, the stoichiometric point, what does it mean to coincide? Happen at the same time, yeah, right? So coincide means happen at the same time or place. So do we want the endpoint to happen at the same time as the stoichiometric point, before the stoichiometric point, after the stoichiometric point, or do we want them both to be at pH 9? They should coincide. They should be at the same point. The last one just seems really random. Why should they both be at pH 9? That's just kind of random. If the endpoint happens before the stoichiometric point, what that would look like is that I should redraw that with a little bit more curve to it. If we have our graph like this, and the indicator changes color here, that means that it's changing color before the equivalence point, and that's not what we want, right? We also don't want it happening after the equivalence point. You know, we don't want it up here somewhere after the equivalence point. We want it to happen at the equivalence point. Yes? Excellent. Next. Yes? 14? The equilibrium concentration of ammonia is 0.5 molar. The pOH of the solution is, so we have x minus x, 0.5 minus x. So Kb is equal to the NH4 plus. You don't have to write all this down. You can just do all this in your head, right? You would write it down for a written response question, but for this kind of question, you can just be like, Kb is equal to x squared over 0.5, because we're going to assume x is insignificant. So Kb is 1.8 times 10 to the minus 5, and that's equal to x squared over 0.5. And that would give us 1.8 times 10 to the negative 5 times 0.5. And we will take the square root of that. And that is 3 times 10 to the minus 3. And that is our concentration of OH. So we're going to take the negative log of that. And that's going to give us our pOH. And that is 2.52. I used Kb because I'm given a base. Yeah? So anytime you have hydroxide, you're going to use Kb. And I say that having marked a bunch of the hydrolysis quizzes and having people had K A using Ka for that. Oopsie. I guarantee you there will be a hydrolysis problem on your test. Okay, everybody's test is going to have whatever version you get, there will be a hydrolysis problem on it. So make sure you know if you hydrolyze and produce hydroxide, you want to use Ka. B, if you hydrolyze and produce hydronium, you want to use Ka. Okay, next. Yes, 18. Which one of the salts will show the greatest amount of hydrolysis if equal concentrations are used? So we have, well, obviously it's not any of the NAs, so it's all the anions. And we're looking at I minus. I minus, does it hydrolyze? No. So it's definitely not A. We have NO2, we have PO4, and we have SO4. All of those are going to act as what kind of substances? What kind of hydrolysis will we get from those? There's only two choices. What are the two choices? Acids or bases. What are those three going to act as? Take a look at them. Do they have hydrogen in them? Are they going to act as acids? No, because there's no hydrogen. Yes? So they have to be acting as bases. Okay, so we're going to get basic hydrolysis for all of them. Basic hydrolysis. Also, 95% of the time, when you have an anion, it's going to be basic hydrolysis. The only time it won't be is if you have an amphiprotic ion that has a Ka greater than its Kb. Okay, so let's just go look at these in terms of their Kb values. And in fact, you know what? I'm going to go back here. And we are going to grab I'm just going to write them down because it's easier than flipping back and forth between the two pages. So NO2, the Ka of the conjugate acid is 4.6 times. Why am I doing this? We can just look. Sorry, because there's no Kb values on this table, it's really kind of stupid. Okay, so we've got la la la. We have NO2, which is here. We have PO4, which is here. And we have SO4, which is here. Which of those will hydrolyze the most? Will it be PO4? Will it be NO2? Or will it be SO4? PO4. Why PO4? Because it is the strongest base. Remember, our bases down here are strong. That is our strongest base. So yeah, it will hydrolyze the most because it's going to have the largest Kb value. It is the strongest base. Did that make sense? Cool. Strongest base hydrolyzes most. All right, next. Yes? 30? Yep. Which of the following equations contains the conjugate acid-base pair from which we can make a buffer solution? Tell your partner the things you need to make a buffer solution. In order to make a weak buffer, what's one thing you need? You need a weak what? Acid, or, so this is your option A. This is option B. You need a weak acid plus what? The salt of its conjugate base. And how much of those do you need? You need both. In how much amount? Just big amount, small amount, medium amount, small amount? Okay, we'll think about that one. We'll think about whether we need a big amount. Or if you don't want a weak acid and the salt of its conjugate base, what else could you have? You could have a weak base. Yep. And the salt of the conjugate acid. And again, you're going to need to have both in either small, medium, or big amounts, and we'll think about that in a moment. Waskaba, Wubska. Weak acid plus the salt of the conjugate base, Wabska. Wubska, weak base and the salt of its conjugate acid. I don't know if that's helpful, but it helps me. Okay, so in these ones here, we have a strong acid, strong acid, strong acid, and now we have a weak acid. Yes? Now, when we write out the equation for a buffer, we do not include the other ion in the salt. We write the net ionic equation. Remember, when we write the equation of the buffer, we would write the weak acid plus water is H3O plus the conjugate weak base. That would be the acidic kind of buffer. So here we have our weak acid. Here we have our conjugate base. And so that is our answer right there. Is good? Okay. Now, going back to our Waskaba, how much do we need of both of them? If you have a tiny amount of this, don't write that down. If you have a tiny amount of that, oh, by the way, how does a buffer work? It works by doing what? By shifting. The buffer works by shifting. Shifting? Shifting. You're either going to use up excess H or you're going to make more OH, or sorry, more H. What's going to limit how far that equilibrium can shift? Like, what if at some point you're going to start shifting and you'll be like, oh, I can't shift anymore. Why would you not be able to shift anymore? you run out, okay? At some point, you're going to run out of the weak acid or you're going to run out of the weak base, and that limits the buffer. That is the limitation of the buffer. So a buffer is, where am I going to put this? Buffer is limited by how much it can shift. If you run out of weak acid or weak base, it cannot shift anymore. So how much weak acid do we need, and how much weak base do we need to have an effective buffer? Do we need a lot or do we need a little? We need a lot, both in large-ish amounts. I mean, they don't have to be huge, but they have to be big enough that you're not going to be like, ooh, I added like 1 drop of acid and I ran out of conjugate base to absorb that, or, you know, large-ish amounts. That was a good question because it kind of reviewed almost everything to do with the buffers. Other questions? 23? Sorry. 23 written? Yes, perfect. Okay, 23 written. What volume of H3PO4 is needed to neutralize? Oh, I think I'm going to grab that question and do it over on the side. Here we go. Give ourselves some space to work. So our H3PO4, we know that we have 0.60 moles per liter, and we don't know the volume. That's what we're trying to figure out. Our NaOH, we know that we have 12 milliliters, and we have 0.25 molar NaOH, or 0.25 moles per liter. Now, this is one of the situations where if you try to use M1V1 equals M2V2 for a titration, you will get the answer wrong. Remember, M1V1 is only for what kind of situation? Is it for titrations? It's for dilutions, okay? No M1V1, okay? Titrations, which is what this is, neutralizations are essentially titrations. And what tool do we use to do a titration equation? We just use stoich. Okay, so titrations, you use stoichiometry. So, what is stoichiometry? In stoichiometry, step 1 What are you finding? Tell your partner. Moles, yes. Step 2, find moles. Oh my gosh, look at that. Step 1 and step 2 are the same, except for you're not finding moles of the same thing. Here you're finding moles of A, which is your known. And here you're finding moles of B, which is your unknown. So anytime you're doing a titration, find moles, find moles. Okay? And then step 3 is going to be find whatever. And in this case, it's going to be liters, although I'm tempted to do it in milliliters. Are you guys okay with using millimoles? Yeah? Okay. So I'm going to say I don't want it in liters. I'm going to use milliliters because then I don't need to convert in and out. Yes? All right. So I have step 1. We're going to find moles of NaOH. So that's going to be 12 milliliters of, oh my gosh, look at this. 12 milliliters of 0.25 molar. 0.25 moles per liter. And that gives us 12 times 0.25 is, what's a quarter of 12? 3? 3.00, or no, 3.0 millimoles of NaOH. Step 1, find moles of A. Step 2, we need to find the moles of H3PO4. To do stoichiometry and convert from moles of one thing to moles of another, what do we need? If I want to cancel my moles of NaOH and find my moles of H3PO4, I need the ratio. And in order to get the ratio, I need to write a balanced equation. Okay, so we have NaOH plus H3PO4. Could you please finish that and balance it? If you have any trouble figuring out the products, it works like a double replacement reaction. You can combine your outside ions, Na plus and PO4 3 minus. And then our inside ions are H plus and OH minus. You do not have to write water as HOH. Sometimes it'll make it balancing easier for you, okay? Up to you. If you have no problem balancing, just go ahead, write H2O. But if you have problems balancing, this will allow you to see that if you have 3 hydrogens here, then you need to have 3 hydrogens here. Yeah? And that means we're also going to need 3 OHs, right? And that means we'll need 3 OHs, which means, oh, look, we have 3 NAs here, and that all works out and life is good. Yeah? So now that we have that ratio, we can say that we have 1 H3PO4 for every 3 NO3, or sorry, not NO3, NaOHs, and 3 divided by 3 is 1.0 millimoles of H3PO4. So that was step 1. That was step 2. Step 3 is find whatever. So in step 3, we have to go back to the question and say, what is whatever? What are we being asked for? We are being asked for the volume. So that could either be milliliters or liters. I'm going to go with milliliters because I have millimoles. So we want to find the milliliters of H3PO4 solution. And let's remind ourselves what we know about the H3PO4. It is 0.60 moles per liter. So we are starting with 1 millimole of H3PO4. We want liters. So liters have to go on the top. We want to cancel moles. So moles have to go on the bottom. And we actually want to keep the milli, right? So we don't want that to go anywhere. So that can just stay there. And we know, oh, hey, look, we know the moles per liter. Whoa, what happened there? That was crazy. Okay, come back here. We know the moles per liter. So 1 liter is 0.60 moles. And we get whatever 1 divided by 0.6 is. 1 divided by 0.6 is 1.67, 1.6 repeater. Oh, don't do that, no. 1.6 milliliters. Excellent. No! How do I make it stop that? There's a setting. Okay, I'm going to close it and then open it again. Huh? Oh! Thank you. You're a genius. Excellent. 1.6 repeater becomes 1.7 milliliters, and there we are done. Okay. Beautiful. Did that make sense, Tree? Yeah? Okay. Anybody want to print out of this one? Nobody? Okay, I'm used to my grade 9s. Yes, I want to print out, everybody. Any other questions? 28 on the written, for sure. I'm glad you guys aren't neglecting the written because honestly, it is the harder part of this unit. Like, I was looking at the average percent. This is like from my old government exams stockpile. The percent, and you guys do usually better than the average percent, so don't let these scare you, okay? But the percent on the multiple choice is usually around 66%. And the percent on the written response, the long answer, is usually about 57%. So I'm glad you're not neglecting the written response. Yes? And by being able to do a question like that, you're like golden, right? Yeah? And by being able to do the questions from the quizzes, you're golden. Yeah? And like I said, I don't mean to scare you because you all generally score above the average. Okay? I've never had classes that have scored the average or below. Okay? I do have people who score below the average, but usually they're the ones who don't show up to class regularly. So, you know. All right, 28. Ooh, more buffers. Exciting. A buffer solution is prepared using H2SO3. What kind of a substance is H2SO3? It is a weak acid. It has to be because this is a buffer. Yes? And what is KHSO3? That is the salt of the conjugate base. Oh, look, it's Wascaba. Yes? Wascaba. Write an equation showing the equilibrium present in this buffer solution. So remember, what you're going to do is you're going to put the weak acid on one side. You're going to put the conjugate base on the other side, and you're going to put water here, and then you're going to put whatever you end up with there, which should, I think, be H3O plus. So we're going to have H2SO3 goes on one side. HSO3 goes on the other side. Remember, you get rid of the spectator. And then who's the other reactant on the reactants? Water. And it should be pretty obvious that the other product is going to be H3O plus. Okay? A small quantity of hydrochloric acid is added to this buffer solution. Complete the following graph of H3O plus versus time to show what happens when H3O to H3O went before the HCl was added until the equilibrium has stopped shifting. So this is before, and it's obviously just staying the same. What happens to H3O plus when we add HCl? It increases. So it's going to go up. Does it go up like this? Does it go up like this? What does it do? It goes up as a spike, right? Because that's our stress. And then, as this equilibrium shifts, this went up. Which way will it shift? Left. What will happen to the concentration of H3O plus? It's going to go down. Is it going to go down like this? Is it going to go down like this? Is it going to go down like this? What's it going to do? Which of those three? 1, 2, or 3? 3. Excellent. Remember, steep, shallow, flat. And does it flatten out at that concentration, below that concentration, or above that concentration? Above. That's why I love this course, because it's all connects to itself the whole way through. Okay, so that one is done. A small amount of NaOH is added to a fresh sample of this buffer. Which of the following statements explains what will happen to the pH as a result of this? So if we add NaOH, first of all, what is that going to do to the concentration of H plus or H3O plus. It's going to go down. Okay, and if it goes down, what's going to happen to the pH? Yeah, the pH is going to increase. So we can say it's either going to be 2 or 3. And then if it goes down, what is the buffer going to do to it? It's going to make it go, or sorry, if it goes up, what's the buffer going to do to it? It's going to make it go back down because it's going to minimize it. So it's going to then gradually decrease. Oh, they both say gradually decrease. Oh no. Is it going to gradually decrease to slightly below where it started? So will it go up and then down, or will it go up and then end up slightly above where it started? Which one's it going to do? It's going to do this one. Yeah? Any other questions? If you don't have any today, I can just give you the rest of class to work on your review. Do you want to do that? Okay. I think tomorrow I will answer any further questions, and then we'll actually start on electrochem just a little bit. We won't get very far, but we'll at least balance. We'll get to be balancing redox reactions because that's a skill you can take with you, and it's pretty easy. Okay, so we'll start that tomorrow. Okay? Huh? You're gonna get the whole book. I'll give you the link to the videos if you're like, I'm taking chemistry next year in university and I would like to know about electrochemistry, and you can go through. I can make sure you have an answer key to go along with that and whatever. Okay? Yeah. Which means we need to run that off today. And the good news is Tyler actually does a lot of teaching for electrochem. Tyler DeWitt.
Oh.
You sound disappointed.
No.
You're like, Tyler, he talks too slow. Just put him on 1.25. He'll be fine.